Now, vapor pressure of liquid solutions. Liquid solutions are formed when solvent is a liquid. Obvious baat hai. The solute can be a gas, a liquid or a solid. Solutions of gases and liquids have already been discussed in section 1.3.2. In this section, we shall discuss the solutions of liquids and solids in a liquid. Such solutions may contain one or more volatile components. Generally, the liquid solvent is volatile. A solute may or may not be volatile. We shall discuss the properties of only binary solutions, that is, the solutions containing two components, namely the solutions of liquid in liquids and solid in liquids. Vapor pressure of liquid solutions. Let us consider a binary solution of two volatile liquids and denote the two components as 1 and 2. So the first component is 1 and second component is 2. When taken in a closed vessel, both the components would evaporate and eventually an equilibrium would be established between vapor phase and the liquid phase. Let the total vapor pressure at this stage be P total and P1 and P2 be the partial vapor pressures of the two components 1 and 2 respectively. These partial pressures are related to the mole fractions x1 and x2 of the, actually it's not x, it's chi1 and chi2 of the two components 1 and 2 respectively. So see, they have denoted here P1 is your partial vapor pressure of the component 1 and P2 is the partial vapor pressure of the component 2, and your chi1 is the mole fraction of component 1 and chi2 is the mole fraction of component 2, and P total is the total vapor pressure of the solution. Vapor pressure at this stage is that basically the equilibrium stage where the vapor phase and liquid phase are at equilibrium. Then Raoult's law, this is again an important point here, right? Raoult's law, which states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. So this is, Raoult's law is basically extension of this Henry's law. Henry's law, we talked about partial vapor pressure of the component being directly proportional to the mole fraction. Now they are talking about partial vapor pressures of volatile liquids. Remember, it is very important for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. Raoult's law states, Raoult's law could be another important one marker. Now, thus for component 1, your partial vapor pressure is directly proportional to chi1, that is mole fraction, and that can be represented as P1 is equal to P1 naught into chi1. This P1 naught is nothing but, they've explained, they would have explained it here. Okay, I don't think so. P1 naught is nothing but the vapor pressure of the pure component, that is P1 is the partial vapor pressure of the component while it is present in the solution, whereas P1 naught is actually a proportionality constant here, which is nothing but the partial vapor pressure of the component when it is pure, that is when it is not present in the solution and it is present independently. That time there would be a vapor pressure, right? That vapor pressure, partial vapor pressure, is represented as P1 naught or P2 naught, or that P naught is nothing but it is the partial vapor pressure of the pure component. So for component 1, P1 is equal to P1 naught into chi1. Similarly for component 2, P2 is equal to P2 naught into chi2. According to Dalton's law of partial pressures, the total pressure over the solution phase in the container will be the sum of the partial pressures of the components of the solution. This Dalton's law we would have learned in our class 11, stating that total pressure of the solution is nothing but the sum of the partial pressure of the pressures of the components of the solution. So we have found that P1 is the partial pressure of component 1 and P2 is partial pressure of component 2. Then the P total, which is the total partial vapor pressure of the solution, total partial pressure of the solution is nothing but P1 plus P2. Substituting the values of P1 and P2, we have chi1 P1 naught plus chi2 P2 naught, which is nothing but they are taking chi1 to be 1 minus chi2, because we know that in mole fraction the mole fractions of the components add up to 1. So chi1 will be equal to 1 minus chi2. So instead of chi1 we are substituting 1 minus chi2 into P1 naught plus chi2 into P2 naught. Solving this, we would be getting, this is actually P1 naught here. Okay, now solving this expression, we would be getting P1 naught minus P1 naught chi 2 plus chi 2 P2 naught. Taking chi 2 as common, we will be getting P2 naught minus P1 naught into chi 2, and then we had this P1 naught earlier, so this expression, so P total would be P1 naught plus P2 naught minus P1 naught into 2. Now this will be your P total expression from the Raoult's law. Now from this equation, there are certain conclusions that is being made. So following conclusions can be drawn from the equation 1.16, which is nothing but your P total expression, right? So first one is total vapor pressure over the solution can be related to the mole fraction of any one component. That is, here see, you can see that only chi 2 is necessary for this equation. Similarly, chi 2 can also be represented by 1 minus chi 1. So total vapor pressure over the solution can be related to the mole fraction of any one of the component. That will be enough. Total vapor pressure over the solution varies linearly with the mole fraction of component 2. As you see here, this total vapor pressure, P total, is directly proportional to the chi 2 over here. That is, it varies linearly with the mole fraction of component 2. Depending on the vapor pressures of the pure components 1 and 2, that is P1 naught and P2 naught is your pure vapor pressure of the pure component 1 and 2. Total vapor pressure over the solution decreases or increases with the increase of the mole fraction of component 1. Depending on the vapor pressure of the pure components 1 and 2, total vapor pressure over the solution decreases or increases with the increase of the mole fraction of component 1. The composition of vapor phase in equilibrium with the solution is determined by the partial pressures of the components. If Y1 and Y2 are the mole fractions of the components 1 and 2 respectively in the vapor phase, then using Dalton's law of partial pressures, we can say that P1 is equal to Y1 into P total, or P2 is equal to Y2 into P total. So in general, it will be Pi is equal to Yi into P total. This is for finding the mole fractions of the components in the vapor phase. That is, Y1 and Y2 are the mole fractions of the components in vapor phase, whereas chi 1 and chi 2 would be the mole fraction in solution phase. So this is what is the difference between that formula, that P total formula, and this formula. So chi 1 is nothing but the mole fraction in solution phase, whereas this Y1 and Yi is nothing but mole fraction in vapor phase. Now, Raoult's law has a special case of Henry's law. According to Raoult's law, the vapor pressure of a volatile component in a given solution is given by Pi, that is nothing but vapor pressure of any ith component, will be equal to chi I, that is its mole fraction, into Pi naught, that is its vapor pressure in its pure form. In the solution of a gas in a liquid, one of the components is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry's law, which states that P is equal to Kh into chi. If we compare the equations for Raoult's law and Henry's law, it can be seen that the partial pressure of the volatile component or gas is directly proportional to its mole fraction in solution. Only the proportionality constant differs from P1 naught. Thus, Raoult's law becomes a special case of Henry's law in which Kh becomes equal to P1 naught. Now, when you compare these two equations, you see that when Kh is equal to your P1 naught, that is Pi naught, then it is nothing but the same equation, right? So Raoult's law will become a special case of Henry's law when Kh is equal to P1 naught. Now this also could be a 2-mark question where they might ask, explain Raoult's law being a special case of Henry's law. Then you will have to say what is the Raoult's law. Basically, Raoult's law is that for vapor pressure of a volatile component, Pi is equal to Pi naught into Xi. Then you need to say that you need to state Henry's law also, and give the equation that if one of the components is so, in the solution of gas in a liquid, one of the components is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry's law, which states that P is equal to KH into chi. Now when we compare both, you need to write all these if they ask as a 2-mark question, that when we compare both the equations, they are the same equation, stating that your partial pressure is directly proportional to chi. Only if there is a difference, minor difference is that there is a P1 not in Raoult's law and there is a KH in Henry's law. So when these two quantities become equal, then both the equations would give the same result, right? So that is why we call Raoult's law to be the special case of Henry's law. Now, vapor pressure of solutions of solids and liquids. Until now we saw liquid solutions. Now we are going to see solid liquid solution. Another important class of solutions consists of solids dissolved in liquid. For example, sodium chloride, glucose, urea and cane sugar in water, and iodine and sulfur dissolved in carbon disulfide. Some physical properties of these solutions are quite different from those of pure solvent. For example, vapor pressure. Liquids at a given temperature vaporize, and under equilibrium conditions, the pressure exerted by the vapors of the liquid over the liquid phase is called vapor pressure. Now this is also important. What is vapor pressure? Right, I've highlighted this part here. So liquids at a given temperature vaporize, and under equilibrium conditions, the pressure exerted by the vapors of the liquid over the liquid phase will be called as your vapor pressure. That is basically the vapor form of the particular liquid when it is vaporized and it has gone above the liquid surface. It will exert some pressure on the liquid itself, right? And that pressure is called as a vapor pressure. In a pure liquid, the entire surface is occupied by the molecules of the liquid. If a non-volatile solute is added to a solvent to give a solution, figure 1.4b, 1 mole of solvent is added to 1 mole of solute. When pure solvent is there, all the particles are occupied placed at the surface. That is, the entire surface is occupied by the molecules of the liquids only. Now when there is an introduction of solute into the solvent, the vapor pressure of the solution is solely from the solvent alone. This vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. When it is a pure solvent, the entire surface is covered with molecules of liquid. Now when there is a non-volatile solute added to the solvent, again the non-volatile solute will not vaporize. So only the solvent will be vaporizing, and it will become its vapor phase, and that vapor phase will exert a pressure on the liquid. That means when then it was pure solvent, let's say, see at the surface, let's say in the pure liquid there were 10 molecules of the liquid entirely covering the surface. Now I added non-volatile solute. I add 5 molecules of non-volatile solute to the surface. Then now there will be 5 molecules of non-volatile solute particle and 5 molecules of the solvent particle. That is, the number of solvent molecules has decreased at the surface. Okay. Now in the pure solvent, the 10 molecules will vaporize and they will become into their own vapor phase, and that vapor phase will exert a pressure on the liquid. All the 10 molecules will do so. When I added the non-volatile solute, this non-volatile solute will not vaporize. Only the solvent particle present there will vaporize. But there are how many particles present at the surface of the solvent? There are only 5 solvent particles present at the surface. That means only the 5 molecules will vaporize itself and will exert a pressure on the liquid called the vapor pressure. Now compare 1.4a and 1.4b. In 1.4a, 10 molecules exerted the pressure. To say that vapor pressure of the 10 molecules exerted the pressure. Whereas in the figure 1.4b, only 5 molecules exerted just because the other one was non-volatile. That means there is a reduction in the pressure. So this vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. That is why the vapor pressure of the pure solvent is greater than the vapor pressure of the solution. Let me continue the video with the NCERT PDF itself. Thought it'd be easy for you guys to look into the pictures and the tables that are represented. Okay, so we were here discussing about vapor pressure of solutions in solids and of solids and liquids, right? So we saw that in pure solvent there are more number of solvent molecules at the surface compared to the solution of a non-volatile solute. So the vapor pressure of the pure solvent will be greater than the vapor pressure of the solution, right? Now, so let's continue from the text here. So we were here. This vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. In the solution, the surface has both solute and solvent molecules. Thereby, the fraction of the surface covered by the solvent molecules gets reduced. As I told you, when we took that, there were 10 molecules here and 5 solute and 5 solvent molecules here. See, there were 10 solvent molecules here. So there is a decrease in the number of molecules that were present at the surface. That is what they're saying here. So in the solution, the surface will have both solute and solvent. So thereby the fraction of the surface covered by the solvent molecules get reduced. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced. Thus, the vapor pressure is also reduced. So that is what the number of molecules that are escaping and becoming as vapors will also reduce, because here all the 10 had got vaporized, then here only 5 will be able to get vaporized. So that is why a vapor pressure was also decreased. The decrease in the vapor pressure of solvent depends on the quantity of non-volatile solute present in the solution, irrespective of its nature. For example, the decrease in the vapor pressure of water by adding 1 mole of sucrose to 1 kg of water is nearly similar to that produced by adding 1 mole of urea to the same quantity of water at the same temperature. So, to find the decrease in the vapor pressure, there is only the requirement of knowing the quantity of the non-volatile solute and not its nature. It can be any non-volatile solute. It should be necessarily non-volatile solute, but it can be any non-volatile solute, but its quantity is what the vapor pressure, the decrease in the vapor pressure of the solvent depends on. Now, Raoult's law in its general form can be stated as: for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. So this is also another question where state Raoult's law's general form, right? General form of Raoult's law could be asked. So that is nothing but, for any solution, partial vapor pressure of each volatile component. So until now we saw that partial vapor pressure is directly proportional to mole fraction. Now we are seeing that for any solution, each volatile component only is directly proportional to its mole fraction. That means for non-volatile component, we are not saying that the partial vapor pressure is proportional to its mole fraction. In a binary solution, let us denote the solvent by 1 and solute by 2. Solvent is always denoted with the number 1. Be it any chapter, be it generally in chemistry, solvent is denoted by the number 1. So in binary solution, let us denote the solvent by 1 and solute by 2. When the solute is non-volatile, only the solvent molecules are present in vapor phase and contribute to vapor pressure. That is what we saw here. If the solute is non-volatile, then only the solvent will contribute to the vapor phase and its vapor pressure. Let P1 be the vapor pressure of the solvent, and solvent we took it as 1, right? So P1 is the vapor pressure of the solvent, then Chi1 will be its mole fraction. P1 not be its vapor pressure in the pure state. Then according to Raoult's law, P1 is directly proportional to Chi1 and P1 is equal to Chi1 P1 naught. The proportionality constant is equal to the vapor pressure of the pure solvent, which is P1 naught. A plot between the vapor pressure and the mole fraction of the solvent is linear. Again, we see that vapor pressure and the mole fraction of the solvent is linear. That means for a solution containing a non-volatile solute and the volatile solvent, then its vapor pressure will purely depend only on the mole fraction of the solvent. So blindly you can use this formula if it is a non volatile solute in a solution. With this, we have come to the end of this video. Thank you for watching. If you found this video helpful, please like and subscribe for more educational content. Don't forget to hit the notification bell so you never miss an update. Your support helps us create more valuable resources for learners like you. Keep exploring and stay curious. Bye.